Hello, welcome again. We are covering the topic centrifugal compressor for civil services main IFS and Gate Aerospace exam. And in this topic, we are doing design of compressor through example. We have solved first question and A part of second question. Now we'll solve B part of second question. So that is your the throat width of the diffuser passage, which are assumed to be of constant depth. Assume that additional frictional loss in the short distance between impeller tip and the diffuser throat is small, and therefore 50% of the overall losses can be considered to have occurred up to diffuser throat. So this is your centrifugal centrifugal compressor diagram, and this is the impeller. Okay. So he, according to his assumption, he asked that up to that point or up to diffuser throat, we can assume 50% of losses. So we can assume this as a part of impeller, okay, and or as a part of veinless space. Okay. The diffuser throat can be assumed as a part of veinless space. So in the veinless space, we have CWR constant. Okay. In the veinless, we have CWR constant, and for the diffuser throat, the radius is 0.3 centimeter. Okay. So CWR is the, so CW2 into 0.3, and that will be equal to uh, the product of burn velocity at the impeller tip into impeller radius. So the burn velocity at the impeller tip is 410, and the radius is 0.25. So we have taken these data from the previous example. So here we have CW2 is 410, and we'll use this data also, that is T02 is 488. So CW2 at the diffuser throat comes out as 211 meter per second. Now, as in the previous case, assume that CR2 is 83 meter per second. In the previous case, we assumed CR2 at the radius of 0.3 meter as 97. So as the radial component decreases further, so now radius is 0.33. So we'll assume a lesser quantity than this and check our assumption is correct or not. So that is CR2 is your 83 meter per second. Okay. Same way, now we can calculate dynamic temperature at the diffuser throat. So that is C2 square by 2 C2, so it will come out as 51.5 Kelvin. Okay. And now the stagnation temperature T02, as we have noted, that is 488, and dynamic temperature is 51.5. So static temperature will come out as 436.5 Kelvin. So now this is the temperature at the diffuser throat. Okay. And this is one component of velocity at diffuser throat, and this is our assumed radial component at diffuser throat, and this is your dynamic temperature. So now we'll calculate pressure. As there is no stagnation pressure loss from the impeller tip to diffuser throat, so P02 by P01 will remain same. That will be your 1.582 rate per 3.5. Now T2 is different. Now we have calculated different T2, and now in this relationship we can replace T2 by this quantity 436.5. Otherwise relationship is same. Okay. So from this P2 by P01 comes out at 3.37, and then P2 can be calculated by multiplying by 1.1, so it will be 3.71 bar. Okay. And from the state equation, rho 2 will be your P2 by RT2, so that is 2.96 kilogram per meter cube. Okay. So here this is your density, this is your pressure, and this is your static temperature. So now after calculating density, we can use mass flow rate. So if we assume this density and take area like this as in the previous example. In the previous example, this was zero point 0.3, now it is 0.33. Okay, so that is so area will be at 25.3 into 0.017. That area is this area, or if we draw a circle and the width is your point 0, or sorry, depth is your 0.076, and the area will be your perimeter into depth. This perimeter, that is zero point 0.3 into depth, so it will come out as 0.0365 meters here. Okay, so now if we check for CR2, down this is your mass flow rate and this is your area and this is your density. So then because this area is perpendicular to CR2, so from this CR2 will come out as 83.3, and we have assumed it as 83, so our assumption is almost correct. Okay, so it will be your 83 meter per second. So now we can find out the direction of flow. So that is your tangent inverse CR2 by CW2. Here CR2 is your 83.3 and CW2 is 311, so that is 15 degree. So now this area we have taken perpendicular to CR2. Okay, so then the mass flow rate is ρ2 ER2 CO2. If we take C2, then area will be A2, because here we have diffuser throat like that. This is not like this. Okay, so it is like this. It is rectangular in section. It has particular depth and it has particular width. Okay, so and the velocity is not a radial, it is C2. So we'll take this area and C2 and multiply by ρ2, and this will give mass for it. So ρ2 is same because fluid is same and place is same. So A2 will come out as AR2 CR2 by C2, and CR2 by C2 is your sine 50, so the angle is 50. So AR2 is your 0.0365. So A2 will come out as 0.00945 meters. Okay. So this is your total area. This is not only of one diffuser, as there are 12 diffuser vanes. So it is of 12 diffuser vanes area, because this we have calculated from the radius and depth. Radius is your 0.33 and depth is your 0.0176, and this will give then total area of 12 diffusers. Okay, and depth of each diffuser is 0.0176. So width will be, because it is rectangular in section and 12 rectangles are there, so it will be width will be 0.0440 meter of 4.4 cm.